Professore, forse deve accendere la registrazione?
Sì, sto aspettando che si collegano tutti. Grazie per avermi avvisato comunque. Facciamo subito, visto che ci siamo. Okay, let's start the class just by recalling what we are doing in these during these last days. We start analyzing the acquisition systems from the signal processing point of view. So we introduce the AD converter, the analog to digital converter, and that is required because everything is working in a C, everything is working with computer programs, so everything is digitalized, and therefore that's the reason why we are staying analyzing these digital signal processing issues that have to be considered when you are setting up your measuring chain. The first signal processing issue is what is called aliasing problem, and this aliasing problem is just the presence of some higher frequency harmonics into your frequency range of interest because of digitalization, because of discretization of your signal, and because you are just viewing your signal with the lens, if you want, of a discrete board. So what happens is that if you are interested up to a certain frequency range, that is up to a maximum frequency, then you have to sample your whatever signal in time domain, so that this sampling frequency allows you to obtain the most accurate synthesis of your whatever signal properties. In order to do that, there is the Shannon's theorem that is helping you in trying to solve this problem. But this Shannon theorem that is just saying that your sampling frequency should be at least twice the maximum frequency of interest, this Shannon theorem is not enough to solve the aliasing problem, because whatever will be your maximum frequency of interest, then your system that is always characterized by an infinite dynamic and infinite frequency content is still aliased by this maximum frequency. Thus, you have also to include the low pass filter that has a cutting frequency that is equal to your maximum frequency, and therefore you solve the problem just by introducing what I call the software, that is the application of the Shannon theorem, and the hardware, that is the low pass filter, to your whatever signal. Then we introduce the leakage. The leakage is due once again to the periodization of the signal in the sample time windows. We saw some example problems, some very nice pictures last class on Tuesday, and we found out that because you are moving from the time to frequency domain, therefore you are assuming that you are taking the Fourier transform of your signal. The Fourier transform algorithms assumes that you are having a periodic signal, and that is not true in reality, because your sample time windows is not generally is not having the whole period of your system, of your signal, but instead if assuming that your signal is periodic with that sample time window, and therefore it introduces some periodization, that is that in the frequency domain you can have what we call a leakage of the energy content of the information of your signal into many frequencies. So how can we solve that? So what is the way of solving this leakage problem? And by the way, this leakage could be considered as the most serious problem with the digital signal process. So it's better that I write down that. So leakage is one of the most serious problem associated with digital signal processing. Okay, and I can advance you that this leakage, okay, errors, okay, right, matter, errors can never be eliminated. So, on the contrary, with respect to the aliasing problem, in which we are solving the problem, practically solving the problem, we eliminate those errors. From the leakage point of view, those errors can never be eliminated. We can reduce them, okay, but there are, okay. So the leakage can be reduced by, let's say, several approaches. Okay, the first one could be using different excitation techniques. With respect to the one that we are considering. For example, we can excite the structure so that your measured signal is having the right periodicity. Okay. The other way is try to increase the frequency resolution. Remember, if you increase the frequency resolution, that means that your observation time, your time in which you are measuring the signal, is going to have very, very large values. Okay, if you have a very high frequency resolution, you will stay there for a long time. That is, you are having your observation period that is practically going to an infinite value. The reason why that could be considered as solving the or reducing the leakage problem. And the third option, the third approach that we are having, is by using what we call windowing functions. Okay. This is the most used approach that we can have. Okay, so this last, the use of the windowing function, is the typical approach that you are having in real life. You can also use the approach A and B, that is change the excitation technique, increase the frequency resolution, but these two approaches are having their own limitations. Okay, you can never change the excitation technique as you like once you are all the mission is set up already there in place, or we can't increase the frequency resolution because you can't wait that much time to have the required value of the frequency resolution. So a good approach is by reducing the leakage errors by using the windowing function. What is this approach? The approach that we are considering, that is the use of windowing function, is trying to reduce the discontinuities that we are fictitiously introducing to your signal analysis because of the required periodizations. Okay, if you go back to your notes and see what happens when you are having whatever sine wave, but is not observed with the right time, what you're having is, once you periodize your measurement, you can see that by moving to one period of time, observation time, to the next one, there is a discontinuity. So the windowing function are just reducing these discontinuities. So discontinuities let me say at the edge of the observation time, so of t, are not reduced. We can't do that much, but are alleviated by two ways. So either by one, by ensuring signal and sampling period are synchronous, or second option, by ensuring that the signal is zero at the start and at the end of the sampling period. Why doing that? Because by doing this, by changing the signal in this way, you are reducing, you are not having any discontinuity at all when your whatever Fourier transform algorithm is fictitiously periodizing your signal. Okay, because at the very beginning, so at the start and the very end, at the end of your observation time, your signal is zero. And therefore, once you periodize this value, this signal, then there is zero with no discontinuity at all. So you are very happy about that. No discontinuity are introduced in your time to frequency domain transformation. However, you are changing a little bit your signal. And that's the reason why you can't reduce, you can't never eliminate these issues from your digital signal processing analysis. Okay, how can we do that? So this second approach, that is by ensuring that the signal is zero at this both end of your sampling time, is assured by applying to your signal what is called windowing function. Okay, so this is assured by applying what is called windowing function. Okay, so we are introducing an additional function, okay, to your measure signal, okay, in order to reduce or to set to zero your signal at the beginning and at the end of your observation time. Okay, how this Windows function is composed? This Windows function sorry, I have to stop for a while. Okay, sorry for this delay. I got an issue, so I have to solve that, and I'm ready. So, what is the shape of this window function? The shape is typically a function that has an amplitude that is modulated, and the resulting is just a sine wave or something like that. Okay, so this window function normally takes the form of an amplitude modulated okay, sine wave. That is, you have your window function that is general function of time, of course. That is something like a0, negative a1, and then one cosine function of the center frequency plus a2 cosine 2 omega 0 t, negative a3 cosine omega 0 t, 3 omega 0 plus a4 cosine 4 omega 0 t plus all the other terms. Okay, and that is true when t is within your observation time, that is from 0 to capital T. On the other side, w dt is equal to 0 otherwise. Okay, and by the way, these coefficients a0, 1, 2, and so on are determined by setting some projection criteria. So the AK coefficients could be reviewed from the from some projection criteria. For example, your WT times some weighting function that is having your form of the shape, parameters, okay, is sort of constant, and that is your weighting function. What can we do with this window function? So what we are having is your whatever signal, okay, your measure signal, xt, times your windowing function is finally called your x w. That is your window function, okay? That is the one that you are going to use when you are dealing with such a problem of periodization, forced periodization, because you are just observing your discrete time function with a limit observation time, okay? And as I said before, the use of window gives rise to errors. Okay. Why that? Because you are changing the signal. You are right saying that you are reducing the leakage because we are setting to 0 your measure signal at the 0 and at the end of your observation time. Okay, but however, you are still changing your your signal, because you are not dealing with just X of t, that is your measured signal, but you are dealing with the XW of t, that is your window measured signal. Okay, and the various, therefore the various types of window distribute your energy or information, that's the same, in different ways. Okay, because just by reviewing your windowing function as amplitude modulated sine wave function, as we just introduced here, okay, as you can see, the window function could be written generally as such a overall function, because of that, by having different values of the coefficients at 0 and 1 and 2, that in turns are obtained by using a sort of minimization of projection criterion, then we have that this change of the signal is changing the way the information is distributed over your signal. Okay, and of course you have to choose your right windowing function according to the different testing, according to the different type of signal that you are considering. So the choice of the windowing function depends on the input, on the input function, of course, and what you have to do. Okay, just to review very shortly some specific properties of such a windows, let me introduce your window function from the filtering point of view, because just by introducing these multiplications of signal, it is your measure signal x times your windowing function w, you are just changing the signal so that you are acting to your measure signal with a different filtering function w. Okay, and the property in the frequency domain of this windowing, that is of your filtering function, that depends on the choice of those coefficients a1, a0, 1, 2, 3, 4, okay, will affect your frequency property of the signal. So let me introduce a very nice, a very well-known plot of the whatever filtering in time in the frequency domain that is representative of our windowing function. So we are having y x-axis, in which we are having the amplitude of your windowing function, so in the frequency domain, so the amplitude in dBs, okay, whereas in the x-axis I have a logarithmic plot of the change of the frequency with respect to the base, to the reference frequency. Okay, so we are having a plot that is something like this. Now I'm plotting that, and then I'm going to discuss a little bit this. What we are having is this shape. Okay, then we are having lower. Okay, something like that. we can identify the 0 dB value that is center to our center frequency, but we are also having here what is called the noise bandwidth. Region in terms of frequency. That is, if you are reviewing this plot as the value of the amplitude or the attenuation that you are introducing to your signal, this frequency range across the center frequency is characterized by the maximum chance of interacting with your signal, and that is why it's called the noise band. Then what we are having is the value here. The amplitude should be the same, and that is called the highest side lobe amplitude. Lobe because we have many lobes, okay? And we have what we call here the side lobe fall off. Okay, so our choice of windowing function is strongly dependent on the windowing function properties in this frequency domain, and these properties are referred to these three, let's say, main characteristics. That is the noise bandwidth, the highest side lobe, and the side lobe fall off. Okay, as you can see, these are characterizing very, very roughly what is the frequency content that is included in your analysis, or it is not included at all in your analysis. Okay, and therefore what we can say, this windowing function varies the amount of energy that is squeezed into the central lobe as compared to the side lobe. Okay, because if you consider the center frequency, all the energy that is across the center frequency is something that is passed to your whatever analysis. What is outside the center lobe, then it is practically reduced. Okay, there is a lot of attenuation, as we can see from this picture. Okay, so let me write that. The windowing function varies, right? Yes, and the amount of energy that is squeezed into the center lobe as compared to that in the side lobes. Okay, and generally, yeah. Okay. What we can say is that the broader the noise bandwidth, the worse is the frequency resolution. Okay, why that? Because it becomes more difficult to pick out adjacent frequencies. Okay, adjacent frequencies. Okay, with similar amplitudes. Okay, and that is quite true, quite obvious, not true, but obvious, because the larger the noise bandwidth, we are treating the same with the same importance frequencies that are close to your center frequencies, and therefore if there is a noise, if there is some differences, you can't select those frequencies. Okay, however, on the other hand, okay, on the other hand, and selectivity is improved with the side lobe fall off. Okay. By the way, selectivity to me means the ability, okay, to pick out a small component. Okay, next to a large one. Okay. And that is the same, the reason for that is practically the same from the other point of view of what we already discussed. Okay. Please know that the side lobe fall off is the slope of this, let's say, straight line that is representative of the side lobes behavior, the peak of the side lobes behavior. Okay, so generally speaking, what we can say is that typically, when referring to window functions, a window function that scores well on bandwidth okay, is weak on the side lobes. Side lobe follow. Okay. So how can you choose between these two parameters? The choice is a sort of trade-off between these two properties. So the choice is a trade-off between the two properties, of course. Okay. Now, having said that, I know that is very, very, very rough, very short. We can stay here for at least 3-4 classes in order to better characterize these frequency domain properties of your whatever window functions represented as sort of filter functions to that. Okay, but for us, it is very important to understand what are the typical shapes of these windowing functions that could be used in our experimental analysis, in our, let's say, structural dynamics analysis that is aimed mainly at the evaluation of your responses, model parameters, and so on. So just to consider possible windowing function, let's see how we can choose. Let me introduce them and how we can choose those windowing functions. Okay, so choosing the windowing functions. We have to distinguish between two types of signals, and these type of signals are belonging to different families, the one of the transient signal family, and the other one is the stationary signal family. Okay, so when referring to transient signals, okay, the typical functions are the uniform, that could be used for general purpose investigation. Force, we will see that how this looks like. For short impulses and transients. Exponential for transients, once again. Which are longer. Than the sample period. Or which do not decay sufficiently within this period, of course. Okay. The typical behavior, the typical shape, sorry, are like that. Okay, this is entire domain, this is the windowing function. The uniform one is something like this, of course. And then one on the y-axis and capital T at the end of observation time. That is your uniform. Okay, then we are having something like that. And that is the force function. It is characterized by a flat first part for a very short duration, and then an exponential part. Okay, and then the other one is the exponential. That is going to 0. at the end observation time. Okay. What is their the main usage? Okay, we will see that the force windowing used mainly for the excitation of the structure, using a hammer. We will see that later. Don't worry about that, but just consider this information. Then you will recap that in a few classes from now. We are considering the exponential windowing, okay, for response signal characterized by a lightly dumb systems, okay, in conjunction with the hammer excitation. Okay, if you want these two, the force windowing and the exponential windowing could be considered as the privilege, the typical windowing for the force and the measurement and the acceleration measurement when doing your model analysis. Okay, and uniform is using, let's say, for reference channels, okay, or specific applications. Okay. Here. Then I just want to introduce, before we go, the other family, that is transient. Now the other family are the stationary signal. Stationary signal are the Hanning window. Okay, and these are for general purposes. Okay, Blackman or the Kaiser-Bessel window. And this type of windows are used if selectivity, you already defined that. Okay, is important. Okay, flat top for calibrating procedures. And then uniform once again. Okay, for special sine waves. Okay, that are characterized, having the period equal to the at least equal to the length of your observation time. The general shape of these functions are this one. Let me plot these functions. Once again, we are having time in the x-axis, your windowing function in the time domain. The rectangular one is center. Okay, let me see here. Negative half t and then half t. Okay, then what we are having the Hanning function. It is something like this. Symmetrical, although it doesn't see. Okay. The Hanning. Then we are having the Kaiser-Bessel function. It is quite similar to this one, but a little bit higher in the value of the center of observation by time. That is equal to 3. And it is your Kaiser-Bessel function. And finally, what we are having is the top, flat top. That is something like this, going down and then up, and going down and then up again. And this is your flat top. Okay, windowing function. And once again, we can have the Hanning function. Okay, for reference, or if you want the input channel, and the response channels. Okay, when we are having a random excitation, no more excitation. Okay, no hammer excitation, but just random excitation. We will see this random and hammer excitation, how they work, so don't worry about that. Just by now, consider that there could be two different type of excitation, by hammer and by whatever random excitation. Okay, time is over. Thank you for your attention. Do you have any questions about this? Okay, so if no questions, I thank you very much. I wish you a very relaxing weekend. See you on Monday, next Monday. Thank you very much. Bye.